Okay, now we'll look at what happens at the inner support, where we get 570. So again, you have to find the shear force at a distance d away from the face of the support, 438. And there also you can find the reinforcement requirement. And here in this region, I have selected 10 millimeter links, which is giving 157. And again, you can see H10 can be provided at 175 centimeters. Now, so basically, if you look at this, you need H8 at 175, here H10 at 175. And here the term H is used instead of T, and H is used for high tensile, high yield bars. So H is the term used, not T. So here you get these H10 bars, here you get H8 bars at 175 spacing. But in the center portion, you don't need to provide that many reinforcement. So what we can do is, we can also find what is the minimum link requirement. We can also find the minimum link requirement and then provide the minimum links in the area where the minimum link carrying capacity is adequate. So basically, we can see that, before that, corresponding to this shear force of 438 kilonewtons, you get a horizontal force of 547 kilonewtons. And to carry this, we need about 3 numbers of H25 at this particular support. So we need about 3 numbers of H25 bars to carry this force. So, and in addition to that, we need the section to be doubly reinforced. Yeah, section to be doubly reinforced. So altogether, 4 numbers of H25 would have to be continued over this particular support. And then we also can see what is the minimum link requirement. And when we provide minimum link requirement, what is the shear force that can be carried? That means in that area, we can just provide whatever the minimum requirement that we selected. So in this area, we can provide the minimum links. To find that, first you have to see what is the minimum ratio that has been specified for shear links. And the minimum amount that is specified for links is given by this equation 9.4. And if you have a spacing S, a link area of ASW, then the shear reinforcement ratio is given by this. For that ratio, the minimum value is given by this equation. So you can say this part is equal to this part. And from that, you can find the equation for ASWOS. ASWOS will be equal to BW times alpha E is equal to 90 degrees for vertical links. And because we generally provide vertical links, so alpha is 90 degrees. But if you have any links inclined, then alpha will be that angle. So alpha is 90 degrees, so sine alpha is 1. So you get ASWS is equal to 0.08 square root of FCK divided by FYK multiplied by BW. So the minimum link requirement will be given by this equation. The minimum link requirement will be given by this equation. ASWOS is equal to BW times this component, and from that we can select a suitable minimum value for links that we are going to provide. Based on that, we can also determine the region in which we can provide the minimum links. So with this, we can find the minimum ASWOS with this equation, and then using that ASWOS here, we can find the minimum shear force carrying capacity. So the minimum shear force ASWS is equal to 0.08 FCK to the power of 0.5, 25 to the power of 0.5, width is 300, the strength of steel is 500, so you get 0.24. And if we select 8 millimeter bars at 300 centers, because we have to be mindful that the maximum spacing of reinforcement is equal to 0.75 D, and the effective depth is 545 millimeters, so we cannot be going for very high spacings. So the spacing that we need in the center part of the beam will be H8 at 300. So we'll select H8 at 300. From that we can find what is ASWOS. That is 100 divided by 300, 0.333. And the minimum value is 0.24. We are providing 0.333. So because we know the ASWOS as 0.333, which is greater than 0.24, that is the minimum value, then we can substitute in this equation and we can find the shear force carrying capacity of the section. So that is 0.333 multiplied by 0.78, depth is 545, 500, hot theta is 2.5, so you get 177 kilonewtons, which means when the shear is varying like this, you can draw the 177 lines, and within that region, we can provide the minimum reinforcement. So in this, we can find the minimum. This way, we can find the minimum reinforcement required. And because we know the loading, we can actually determine the location of the distance from left-hand side support and the distance from right-hand side support to get this to this value of 177. So only a small portion of the beam, 1.16 meters from this side, 1.9 meters from this side, so it's about 2 meters and 1.4 meters in this region, you will be able to provide nominal links, which is H8 bars at 300 centimeters. So this way you can provide reinforcement in a beam. But in addition to all this, you have to again think of another aspect when you are dealing with flange beams, and especially in the case of when you are designing inverted T-beams, we have to be concerned about this particular requirement. And the requirement is that we'll get some shear between the web and flanges of T-sections. So when you are using T-sections, there can be a variation of the load in the flange because the bending moments are changing, and most of the bending moment is carried by the flange. So when the bending moment is changing, the force in the flange also changes, and because of that reason, we can have some shear acting in between the flange and the web. So here you can see the flange also carries some force, and as the bending moment is varying, the force in the flange will increase. So when the force in the flange is increasing, if you consider the equilibrium, here you get one force, here you get that force plus another component, and this additional component is going to cause some shear here, and that shear has to be resisted by the reinforcement that we provide within the flange width. So there are three things you have to decide. First thing is, whether the flange concrete can crush due to this particular shear, which is very unlikely, but still you have to check it. Then we also need to know whether we need reinforcement, and if we need reinforcement, how much reinforcement we have to provide. So to determine that, you have to consider the bending moment difference, and to determine the bending moment difference, a recommendation has been made. The maximum value for delta x, that is the distance that you are going to consider for this change in bending moment, the maximum value for delta x, that is this distance, may be assumed as half the distance between section where the moment is 0 and where the section is section with maximum moment. So basically what you are saying is, so when you have a bending moment, so if you have a simply supported case, bending moment diagram like this. So this is the place where you get the maximum moment. Here you get 0 moment. And so if it is A, consider A by 2. So when you consider A by 2, we have to see which part gives the maximum moment difference. And here you can see this part gives the maximum moment difference, not this part. So we have to just decide that, the moment difference you have to consider is this. But if you have a continuous bending moment diagram, then you can on the computer, if I use computer to find the bending moment, you can find this distance using the computer generated bending moment diagram. And find that distance by considering the computer generated bending moment diagram. So you don't have to do any calculation, but here I'll make use of an example of a simply supported beam and show you how to calculate this reinforcement. So basically we need some reinforcement this way, and that is to prevent any failure that can occur between the flange and the web. And so the one important parameter is what is the distance that we are going to consider the change in moment. What is the distance that we are going to consider the change in moment? And then if we need some reinforcement, then the reinforcement that we have to provide is given by this equation. And here you can see the steel area is given, the spacing of the reinforcement is given, ASF, and the height, HF, is the thickness of the flange. So if you need this reinforcement, that will be decided by the value of VED. And then the other important thing is, although unlikely, you have to still check this, and that is the possibility of this flange concrete crushing due to the shear caused by the force difference between the flange and the web. So we have to check that. So we have to check the possibility of crushing. And if the flange is in tension, the angle changes. The variable angle is from 38.6 degrees to 45. But most of the time flange will be in compression. So if the flange is in compression, then the angle will vary between 26.5 and 45 degrees. And tan 26.5 is 0.5. And so tan 26.5 is 0.5, and cot 26.5 is 2. Cot 26.5 is 2. So first we'll start by looking at 26.5 degree angle. So then we also need to know how to decide whether this reinforcement is needed or not, or whether we have to design the reinforcement or not. And that is decided by this equation. If VED is less than or equal to K times FCTD, no extra reinforcement is needed. And the value of K is 0.4. And FCTD, I'll show you how to calculate that in a moment. And that is the tensile carrying capacity of concrete, the design tensile force carrying capacity of concrete. And this is the design tensile force carrying capacity of concrete. So again, you can see it depends on the tensile force carrying capacity of concrete. And so what we are going to say is, due to the variation of bending moment, there will be a change in the force in the flange, and that change in the force in the flange can cause certain amount of shear between web and flange, and that shear may lead to crushing of concrete. That we can check by deciding the maximum force in concrete, or maximum stress in concrete. And then we also need to decide whether we have to provide this reinforcement, and that is decided by checking the VED value, allowable VED value. And if this stress is high, then we will need the reinforcement as well. Then we can calculate the reinforcement. So that is the method. So we look at an example, again taken from a book. A simply supported beam has a span of 6 meters and has the flange cross section shown in figure 712. So it's a small flange, only 600 millimeters wide. So characteristic material strengths are 25 megapascal, 500 megapascal for steel, and subjected to not a massive load, only a small load, 44 kilonewtons per meter. So this is simply supported. So the maximum moment at the span is WL squared over 8, which is 198 kilonewton meters, and for that you can find the reinforcement. And the reinforcement is found as 905 square millimeters, which can be provided by having two numbers of H25 bars. And when you calculate the reinforcement ratio, it's more than the minimum ratio that we have to provide. So the steel percentage is greater than the minimum specified. And then we are coming to the important parameter that we are looking at. And that is, how much reinforcement that we have to provide this way. And for that, we have to make use of this equation. And so the first thing that we have to decide is, what is the maximum moment? What is the zero moment? What is the moment halfway through that? And that means, we need to know the moment at, if the span is L for the simply supported beam, we need to know the moment at L by 4. We need to know the moment at L by 4. So that can be found by using a simple equation like, in a simply supported beam, the bending moment at any location is given by WL by 2 times X minus WX squared by 2. So WL by 2 X, and X is L by 4, minus WL squared WX squared by 2. Sorry, the bending moment at any location is given by WL by 2 times X minus W times L squared by WX squared by 2, and instead of WX squared by 2, it's given as WL WX times X by 2. So that's why you get L by 4 and L by 8. So the final answer is 149 kilonewton meters. So basically, the bending moment changes from 0 to 198 when it comes to the middle point. But when you consider the first quarter, the bending moment changes from 0 to 149. So the maximum change in the bending moment occurs from 0 to 149 over L by 4 from the support. So the change in the force, longitudinal force in the flange wave interface is given by the change in moment divided by the lever arm, change in moment divided by the lever arm. So lever arm is D minus HF over 2, D minus HF over 2, and then we have to multiply it by the width of the flange, on one side divided by the total width of the flange. So basically what you have to do is, we have a flange beam and we have to find this portion, and this BW, this B flange, and that is B flange minus BW divided on BW divided by 2. So that is the width. So delta M divided by, here you get D minus HF over 2 will give the total change in force, and then you have to find what is the change in, so this is the total change in force over this full width. Then you have to find what is the change in force only in this portion, that is BF minus BW divided by 2 divided by BF. So that is the total change in force. And earlier WL by 2, and if you take any section WL by 2, X minus W X squared by 2, and WL by 2 times L by 4 minus W L by 4 multiplied by L by 8. That's how it was written earlier. So this delta M, this M at L by 4. So this is the bending moment at L by 4. That is the early equation we discussed. And the force in this area is given by this equation. So that way we can find the reinforcement needed. So the force needed. So BF4 in this particular case is 600 millimeters. 600 millimeters. And this width is 250 millimeters. So you can see 600 minus 250 divided by 2 divided by 600. And here the effective depth is 530. And the thickness of the flange is 150 divided by 2. And you'll find that the total force that has to be resisted over a length of L by 4 is 96 kilonewtons. Is 96 kilonewtons. And the span of the beam is 6 meters. So L by 4 is 1.5 meters. So we get 1.5 meters for L by 4. And which means we can find the longitudinal stress induced between the flange and the web, and that is total force difference divided by the area. And the length of the beam we consider delta x is 1500 or L by 4, and the thickness of the flange is 150. So you can find that the stress induced is 0.43. Stress induced is 0.43. Stress induced is 0.43. And from that, we can find whether we need the reinforcement or not. But before finding that, we'll also see what is the stress in the what is the maximum stress that can be allowed, because we know 0.43 is acting and we know 0.43 is not a big amount. And we also see whether we also need to see whether the concrete can crush, and also we need to see whether the reinforcement is needed. So 2 more checks to be done. And what we have found up to now is only this force VED value from the bending moment diagram. Now we have to see whether concrete can crush, and then reinforcement is needed. If the reinforcement is needed, we have to use this equation and find the reinforcement. So that is the method. But it's very unlikely that anything serious will happen here. So the maximum stress in concrete, and that is given by this equation. And nu is 0.6 times 1 minus 250 something, that equation. And FCD is FCK divided by 1.5. And sin theta cos theta can be replaced by 1 over cot theta plus tan theta. So we look at that equation. The value of nu is given by 1 minus FCK over 250 multiplied by 0.6 FCK, and FCD is equal to FCK divided by 1.5. Sin theta cos theta is equal to cot theta plus tan theta, 1 over cot theta plus tan theta. So the angle varies from 26.5 to 45. Tan 26.5 is 0.5, and the corresponding cot theta is 2. So the addition of these parameters is 2.5. So that is 2.5. 2 plus 0.5. 0.6, FCK is 25. So once you substitute, you can see the crushing strength of concrete due to shear is about 5.4 newtons per millimeter squared. And generally we know the crushing strength of concrete in shear is around 5 newtons per millimeter squared. So we are getting 5.4 in this particular case, which is okay. So the concrete can crush due to shear at a stress of 5.4 newtons per millimeter squared, but what we are applying is only 0.43. What we are applying is only 0.43, so nothing to worry. There cannot be any crushing of concrete. Anyway, crushing of concrete is unlikely in this type of lightly loaded beams. Crushing of concrete can happen only if the concrete is heavily loaded, like in the case of a foundation. This might happen, but not in the case of a normal beam. So the angle varies between 38.6 and 45. Sorry, 26.5 and 45. But if the flange is in tension, it varies between 38.6 and 40. So it varies between 1.25 and 1. Whereas in this particular case, it varies between 26.5, which is cot theta is 2 to 1. So variation is 2 to 1. Earlier, the variation is was 2.5 to 1. In the case of pure shear, direct shear, the variation is from cot theta varies from 2.9 to 1, and here it varies from 2 to 1. If the flange is in tension, it varies from 1 to 1.2. So then the next question is to find whether we need to provide reinforcement, and to see whether we have to provide reinforcement, we need to find this particular limit, 0.4 times FCTD, and let's see how to find that. If you look at table 3.1 of if you look at table 3.1 of Eurocode 2, there's a table given, and in that table all these FCTM, FCTK, all those values are given with the equation. So FCTM is 0.3 times FCK to the power 2/3, and FCTK is 0.7 times FCTM, and from that you can actually find the value of VED. So what you do is, first we'll see what is this value, and that is 0.3 multiplied by 25 to the power 0.667. So you get a value of 2.56. 2.56 multiplied by 0.7 is 1.79 or 1.8. 1.8. So this value is 1.8. And if you want the design value, then we have to divide this value by 1.5. So you get 1.8 multiplied by 0.4 divided by 1.5. And 0.4 divided by 1.5 is 0.27. 0.4 divided by 1.5 is 0.27. Here you can see that value has been used. And FCTK is 1.8 for 25 megapascal concrete. So it's 1.8 for 25 megapascal concrete. 0.4 divided by 1.5 is 0.27. So VED is equal to 0.27 multiplied by 1.8, which gives a value of 0.27 multiplied by 1.8 gives a value of 0.49, 0.486 or 0.49. So you can see VED limiting value is 0.49. The stress that is acting due to this flange action is 0.43, which means we don't have to provide design reinforcement. There's no need to design the reinforcement. If we just provide nominal reinforcement, it will be adequate. And then we'll just provide the nominal reinforcement, not the design reinforcement. And if this value is 0.49, this value is about 1, then we have to design the reinforcement. And if we have to design the reinforcement, that value is about 1. What we do is we substitute in this equation as 1, and then the area of reinforcement, generally if you are using 10 millimeter bars in the slab, it is 78 millimeters, 78.5 millimeters squared. This 500, the spacing, say 150, substitute, or you can just find the spacing required when the diameter of the bar is known. And this thickness is 150 that we know, and cot theta is cot 26.5, which is equal to 2. So straight away we can find the reinforcement spacing when the reinforcement area is known. And here the area will not be doubled, it will be the area, because we have only one reinforcement, not two legs as in the earlier cases. So basically we don't need any special reinforcement. We can just provide the nominal reinforcement. Or if you are designing the slab to carry hogging moments over the beam, then we'll be providing that particular reinforcement in the slab, and that will be adequate. We don't have to provide any extra reinforcement. But if we need this reinforcement, and in addition to that we have already designed the reinforcement in the slabs for hogging conditions, then what it says is we have to provide the case of combined shear between flange and the web and transverse bending. The area of steel should be the greater than that given by expression 621. Either you have to provide this, or half that is given by this expression plus what we need for the bending in the slab. What we need for bending in the slab. So either provide this or provide half of this plus what we need for bending in the slab. So that is what you provide if we need reinforcement to resist the failure between flange and the web. So in most of the cases, in normal situations, what you find is, we design the slab to carry hogging moments, and because of that we need reasonable amount of reinforcement. And anyway, in most of the normal cases, the beams are not heavily loaded, so most of the time you will find the stresses are also low, and the provision of that reinforcement is sufficient, and generally we don't check it. But in the case of foundations, because they are heavily loaded, then you might find that this situation can be more critical in the case of foundations, especially in the case of inverted T-type foundations. So we have to actually check this particular requirement, and that is the amount of shear that can occur here, and whether the concrete can crush in the flange, and also whether we need reinforcement or whether concrete alone can carry it with minimum reinforcement. Or else, if you are needing some reinforcement, then we have to increase the reinforcement requirement in addition to the reinforcement that we calculate to carry the hogging moment at this location. So in the case of inverted T-type foundation, it will be the sagging moment that occur here. So we'll find, when you invert this, we'll find some bottom reinforcement. And in addition to the normal bottom reinforcement, we might have to provide some additional bottom reinforcement to resist the failure between the web and the flange. So that is the importance of this particular component for the design of inverted T-type foundations. So that's why, I spend little time highlighting the requirement. And also when it comes to inverted T-type foundation, if you do a model with springs, then you can always find the bending moment diagram. When you know the bending moment diagram, you can always find the location of zero moment and the maximum moment. And from that, you can work out what is the moment change between halfway mark from zero moment. What is the moment change from zero, from what is the moment change at halfway mark from zero moment? So that can be actually calculated from the bending moment diagram that you get from the computer program. So that is one important aspect. And in addition to that, you have to actually provide the minimum reinforcement that is needed. And the minimum reinforcement that is needed is actually given by this particular equation. Equation 9.1 of Eurocode gives the minimum reinforcement that you need. And that again, you can see a function of FCTM. And FCTM is given by this equation. It's a function of FCTM. And that is the tensile capacity of concrete, the mean value. So FCTM, that can be calculated by using that particular equation, and the strength of reinforcement. So generally for 25 megapascal concrete, you will find that the reinforcement requirement is the minimum 0.0013. But when you are using higher strength concretes, you will need more reinforcement than 0.0013. So the amount of the minimum reinforcement that you need actually depends on the grade of concrete that you are going to use. It depends on the grade of concrete that you use. And once you find this minimum reinforcement, any secondary reinforcement that you need can be 20% of the main reinforcement. So the reinforcement that you provide as secondary reinforcement can be 20% of the main reinforcement. And then the minimum requirement in columns and walls are also given in this table. So basically, when you substitute this one, earlier we calculated this value for grade 25 concrete. So that is 25 to the power 0.667 multiplied by 0.6. So you will find it is multiplied by 0.3. So that is 2.56 and 2.56. And when you substitute in this equation, 2.56 divided by 25 multiplied by 0.26. So that is 25 to the power 0.667 multiplied by 0.3, 2.56. And FYK is 500. So divided by 500 multiplied by 0.26. So you get 0.0013. You get 0.0013. So this is 500. This is the value that you calculate from the above equation. And for when you have grade 30 concrete, 30 megapascal concrete, so it comes to 30 to the power 0.667 multiplied by 0.3. So you get 2.89. And once you substitute in this equation, 2.89 divided by 500 multiplied by 0.26, you will end up with 0.0015. 0.0015. So you'll end up with 0.0015 when you use this equation for 30 megapascal concrete. For 25 megapascal concrete or 25 cylinder strength concrete, 25 newtons per meter square cylinder strength concrete, you get 0.0013, and which means you have to provide that particular reinforcement in the transverse direction. And so 0.0013 is equal to has to be multiplied by the breadth of the flange and the thickness of the flange. And when you use 0.13, you have to divide by 100, so it's 195 millimeters square per meter. And the area of a 10 millimeter bar is 78.5. So you need about 2.48 bars. So you can provide 10 millimeter bars at 300 centers. 10 millimeter bars at 300 centers, and that is the nominal reinforcement. But if VED value that you calculated had been about 1 Newton per millimeter square, then we have to actually calculate the amount of reinforcement. So, any questions on that? And you will see that this is generally you might not be performing this calculation, but this particular calculation to determine whether we need extra reinforcement here to resist the shear between flange and web has to be performed, and this may be particularly important in case of foundations, inverted T-type foundations, because the loads will be higher. So any questions on this, please? So some feedback, please. Dilisha, could you understand? Amarakon? Hirandi, can you understand this? Dasul? Nishan? Amir? Anybody who can give some response?
Sir,
yeah.
Is there any similar calculation also?
Where? What is that? What is the question?
Is there any similar calculation in the BS method also?
Actually, BS code was not very particular about this, except for composite construction and so on. They were particular, but not in the normal. The reason is in BS, because they consider this flange beam. When you have the flange action, it is the in situ cast construction. You get generally, this is not a very serious situation under normal conditions, because we'll have a lot of hogging reinforcement which will be continued, and also in addition to that you will have the bottom reinforcement also continuing onto the beam. So when we provide reinforcement in a slab, we get the bottom reinforcement continuing over to the beam, and we have the top reinforcement to resist the hogging moment. So you have two mats. So because of that, this failure is very remote. So that's why the BS code, it was not particularly highlighted. But if you look at this code, these Euro codes are written covering all aspects. They are not written, these clauses are not for one particular type of structure. It covers all the different possibilities. So that's why, they have included this particular calculation here. Because, if you have only one method of reinforcement, then they can be failures. But in the normal beam slab construction, always we get two methods of reinforcement. And because of that reason, this kind of failure is very remote. But whereas in the case of foundation, if you decide to provide only the bottom reinforcement, then this can be a critical situation. So that's why, it's not specifically covered, because BS codes are written for, say, for bridges, one code, for buildings, another code, and so on. So, whereas in Euro codes, whether it's a building or a bridge or whatever the structure, it's the same code. So that's why, they have covered all these different situations specifically. Is that clear?
Okay, sir.
So any other question? So I have given some tables from books, because this code does not give any information. So sometimes, it's worthwhile for you to get this information and convert all these detailed calculations to spreadsheets, so that, you can straight away use the spreadsheet to perform the calculation, because all these are coming with equations. All these values come with the equation. So because the equations are there, you can easily convert all these to spreadsheets. So shall we take a break and then start talking about the punching shear? Okay. So we'll take a 10 minutes break. So we start at 4:15.